Hello, my name is Alberto Ortega, and I'm part of network team number one. In this final oral exam, I will present the complete solution that our team developed to incorporate the multi-site network project. Throughout the training unit, we progressively built a fully functional and secure enterprise network connecting several offices and production centers across different cities. Each stage focused on different layer of network, from the physical and logical design to VLAN segmentation, routing, NAT services, MPLS, style interconnection, and finally the implementation of security schemes. Hold on a minute, just let me put a timer. Okay. The presentation will follow the exact order requested to the professor. We're going to start with physical network design, the logical network design, and using VLSM, VLAN OSPF, and DHCP, NAT and MPLS integration and implementation of security schemes. I will also show the packet tracer topology during the explanation to visualize how each stage evolved and how everything fits together. Now I'm going to start with section one, the physical network design. Let me begin with section one, which is the physical network design. This stage was essential because it established the physical structure that will later configure would rely on. We were first asked to carefully read the problem statement to understand the corporation's physical connectivity needs. This included the number of office locations, and production centers, the necessary interconnection devices for each site, the required terminal equipment such as PCs, servers, and printers, and the type of connections planned for each building and one connections linking offices to production centers. The instructions also emphasize the importance of using clear visual organization in packet tracer. We need to assign colors, labels, interface names, and meaningful device naming conventions to maintain clarity as the topology grew. Now I'm just going to show the topology, the physical design, which is this one here. As you can see, everything is in different colors. We also have labels like Guadalajara Production Center, Guadalajara Office, Querétaro Production Center, the Querétaro Office, Monterrey Office, Saltillo Production Center, Leon Office, and Silao Production Center, and finally the Ciudad de Mexico headquarters. So each color block visually represents a different geographical region, which greatly improves readability. Inside each region, we placed one main router as the default gateway device, one switch providing LAN distribution, various terminal devices like PCs, laptops, PCs, the laptops, and servers, printers, and the required serial interface, connecting the different office with its associated production center. The WAN links between office and production centers were configured using PPP serial connection, following the instructions that emphasize using point-to-point WAN technologies. We also followed a consistent naming convention for every device. For example, routers associated with the office were named RTR City, while production centers routers were named RTR City PC. Similarly, switches were named SW City or SW City PC. This consistency was extremely useful when configuring the routing VLANs, NAT, and ACLs later, as we could quickly identify each device's purpose in the topology. Furthermore, this stage required us to limit the number of terminal devices shown in the diagram to prevent visual clutter. Only representative devices were included, while the conceptual structure remained scalable. In summary, this physical design served as the architectural foundation of the entire project. Every layer of the network, addressing VLAN segmentation, dynamic routing, NAT, MPLS, style connectivity, and security, was built upon this topology. Okay, so now I will move on to the section two, which covers the logical network design using VLSMs. This stage is extremely important because it transforms the physical diagram into a structured and scalable addressing plan, allowing the network to function coherently, grow over time, and support all the services that will be added later, such as VLANs, routing, NAT, and security policies. When addressing an enterprise network, the logical addressing schemes is essentially the language that allows all devices to communicate reliably, without conflict, without overlaps, and without ambiguity. So therefore, this stage requires to think carefully not only about the current requirement of the corporation, but also about the future requirements, especially because the instructions explicitly indicated that we needed to include a 30% growth factor. So for the requirement analysis, the instructions for this stage required us to identify all the network segments that each city needed, assign a private IP before block to each city, apply VLSM, to divide the block into subnets and appropriate sizes. Design separate subnets for each VLAN, ensure point-to-point links used /30 networks, leave space for 30% additional growth, and organize everything in a clear and structured addressing table, and document the entire plan in a PDF spreadsheet that you can see here. So this means we couldn't just assign random subnets. We needed to assign a hierarchical, and scalable structure that made logical sense and was easy to reference during later routing configurations. So now I'm just going to be explaining a little bit of the general addressing strategy. Our team decided to use the private block 172.16.0.0/12, but to maintain consistency and clarity, we allocated a unique /16 block per city. This resulted in Ciudad de Mexico being 172.16.0.0/16. Guadalajara is 172.16.1.0/16. Monterrey is going to be 172.16.4.0/16. Querétaro 1.72/16/16.2.0/16. León is going to be 172.16.3.0/16. And the production centers, additional dedicated subnets within their per city blocks. Assigning a /16 per city may seem like an overkill, but it was intentionally done to satisfy growth requirement, to ensure predictability, reduce administrative overhead, and make the network easy to manage as the organization expands. This also ensured that every IP inside a city is easily distinguishable from an IP inside another city. For example, any address starting with 172.16.4.x clearly belongs to Monterrey or Saltillo. This structure dramatically simplifies routing tables and troubleshooting later. Per VLAN subnet and allocation. Inside each city, we created 4 main VLANs. The VLAN 10 is going to be the corporate or server VLAN. The VLAN 20 is going to be the employee VLAN. The VLAN 30 is going to be guest VLAN. The VLAN 40 that you can see here is going to be the OT VLAN. And VLAN 99 is going to be IT administration or management VLAN. Each city has different host requirements. For example, employee VLANs require the most addresses. Guest VLAN requires fewer. Server and management VLANs usually have very small footprints. Based on this, we used VLSM to allocate /26 subnets for employee VLANs that holds up to 62 hosts plus 30% growth, /27 and /28 subnets for server and management VLANs, and a dedicated /30 subnet network for WAN links. This precise allocation allowed us to avoid wasting addresses and ensure efficient IP usage. So for the WAN links, another major part of this design was defining the point-to-point WAN links. WAN connections only require 2 usable addresses, one for the office router and one for the production center router. For this reason, the most efficient subnet to use is /30, which provides exactly 1 network address, 2 usable addresses, 1 broadcast, and it doesn't waste anything. We assigned /30 networks systematically so we could immediately identify WAN segments in routing tables. This helped us tremendously during the OSPF implementation and next section. One of the most important decisions in our logical design was adopting a first usable IP as gateway convention. This means that for every subnet, the router gateway uses 0.1 or the first available usable address. For example, VLAN 10 in Ciudad de Mexico might be 172.16.0.0/27. It's going to turn the last 0 into 1. And for VLAN 20, it's going to be 172.16.0.128. And the way that gateway instead of 128 is going to be 129, and so on. So this consistency is extremely helpful when configuring hundreds of interfaces across dozens of routers and switches. It avoids confusion and makes troubleshooting significantly easier. For the naming conventions, the logical design was documented in a structured Excel, as you can see in the back. This spreadsheet includes VLAN names, subnets, masks, gateway, usable IP ranges, broadcast addresses, WAN networks, public NAT mapping, reserved subnets. Without this logical plan, the next usage VLAN configuration, OSPF routing, NAT configuration, and ACL rules would have been impossible to execute them correctly. Lastly, I just want to emphasize that this logical design is not just an academic exercise. In real organizations, badly planned addressing leads to network fragmentation, waste of IP ranges, difficult scaling the networks, and major security issues. By contrast, a good addressing prevents overlap, simplifies DHCPs, helps NAT configuration stays organized, and yeah, this makes the network more secure and easier to troubleshoot. To summarize, the logical network design using VLSM allowed us to create a structured, organized, and scalable addressing plan for entire corporate networks. This plan defined the gateway address DHCPs, scopes OSPF network statements, not inside addresses, and ACL ranges that we used later. And with both the physical and logical layers now fully defined, the network was ready to the next major step project, implementing VLAN, OSPF, dynamic routing, DHCP services. So now I will continue with section 3, which covers the configuration of VLAN, OSPF, dynamic routing, and DHCP service throughout the entire multi-site corporate network. This stage marked a major turning point in the project. Up to this point, everything we had done was conceptual. We designed the physical topology, and we created a logical addressing plan using VLSMs. However, in this stage, the networks transitioned from being purely theoretical to become fully operational. Once this section was completed, every city in the corporation, office and production centers became interconnected, routable, and functional as a unified enterprise environment. This stage essentially turned on the network. So first, we're going to understand the requirements. The instructions require us to carry out several key tasks. So to create VLANs on all switches, assign the switch interfaces to correct VLANs, configure trunk ports between switches and routers, create router sub interfaces using .1Q encapsulation, configure OSPF area 0 by dynamic routing, implement DHCP pools for dynamic address and assignment, perform connectivity tests across all the cities. This is a substantial number of configurations, and doing them consistently across a large network requires discipline, precision, and planning. The logical addressing plan created in section 2 was essential here. Everything we did from this point onward depended directly on the correctness of the VLAN IDs, subnet mask, getaway assignments, and addressing structures we developed earlier. For the creation of all sites, I'm going to show you the packet tracer. The first step was to create the VLANs on all switches. We configured the standard VLAN across the all cities VLAN 10, the 20, 30, 99 that we talked in the last section. As you can see here, we also have the VLANs here, the VLANs here. We have the VLAN here, 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 and here. We kept this VLAN ID consistent across every location in the network. This is a critical best practice because identical VLAN numbering simplifies trunking, routing, NAT mapping, ACLs, and documentation. Once the VLAN were created, we assigned switch ports to the correct VLANs. Servers were placed in VLAN 10, workstations were placed in the 20, the guest devices and test endpoints were placed in VLAN 30, routers, IT devices, and management workstations were placed in VLAN 99. So this consistent segmentation immediately provided logical separation of traffic. For example, employees cannot access management devices directly. The guest users are isolated, so they cannot reach corporate resources. Servers are protected in a dedicated VLAN with control access. And this type of segmentation is a key principle of secure scalable network design. After defining access ports, the uplink between each switch and router needed to be configured as a trunk port. The trunk allows multiple VLANs to share the same physical interface by tagging frames using the 802.1Q encapsulation standard. All switches were configured with switch port mode trunk. Switch port trunk allowed VLAN 10, 20, 30, 99. This ensured that all VLANs could travel throughout the trunk to router without this step. The sub interfaces on the router would receive untagged traffic, causing misrouting, DHCP failures, and incorrect inter-VLAN communication. Trunking is the essential bridge between layer 2 VLANs and layer 3 routing. The routing on a stick implementation. So now we move on to the routers. Since each site only has one physical interface leading into LAN, the routers must sub-interface to route traffic or multiple VLANs. This configuration is commonly known as router on a stick. For each router, we configure sub-interfaces like jig 0/0.1.2.3.99 for it, depending which VLAN we have. We can see the connections here. The jig 0, you cannot see it, but it was there a minute ago. Well, each sub-interface used .1Q encapsulation for it was encapsulation .1Q, these symbols, VLAN ID. And each was assigned to the corresponding default gateway for the VLSM plan. For example, the jig 0.1, its IP was 172.16.x.1. The point 2, it was the same, 172.16.x.129. The other one was the point 3 was 172.16.x.97. And lastly, the jig 99 was 172.16.x.33. This gateway consistency across all the cities greatly simplified the ACL creations in section 5. configuring the OSPF area 0, the backbone of the network. So with the OSPF was a crucial component that made all cities part of the same routing backbone. Without the OSPF, the network would remain isolated and would not function as a unified system. We configure OSPF with the router OSPF1 network subnet wildcard area 0. Every VLAN subnet in every 1/30 subnet and every intercity network was included in the OSPF configuration. Now, for the DHCP configuration, with routing in places, the next step was to configure DHCP pools for VLAN 20 for the employees, and in some cases, VLAN 30 for guests. For each router, we configured the IP DHCP excluded address, reserving static IP DHCP pool VLAN 20, the network subnet mask, the default router, gateway, DNS server, and DNS. And for connectivity testing, once the VLAN, the OSPF, and the DHCP were configured, we performed comprehensive set of connectivity tests. This included pinging between devices inside the same VLAN, pinging across the VLANs, pinging the office routers, from the PC in one city to the server in another one, and verifying the default gateway assignments, testing testing DNS if applicable. So to summarize this section, 3 was the point at which the network came to life. The combination of VLAN segmentation, OSPF dynamic routing, and DHCP automation created enterprise-grade environment that is scalable, organized, and efficient. Now that the internal network was fully functional, the next stage involved connecting it to the outside world through NAT and implementing secure public access to internal services. But before I leave, I just want to show the pings we did here. As we can see, we have the gigabit with its IP address, like I just said. We have all the configurations here, and I want to show you the pins. As you can see, we are pinging right here from RTR Ciudad de Mexico to the server, from ISPR router Ciudad de Mexico to the internal server of Ciudad de Mexico, from router Ciudad de Mexico to MPLS SW to intercity routing, from RTR Guadalajara PC to server from Guadalajara PC. Here we have from router Guadalajara to MPLS switch, from PC Internet Guadalajara to ISP router Guadalajara. As you can see, all the pings here were made, and we received a reply, meaning that it was correctly connected to each one. Now I will continue with section 4, which covers the implementation of NAT and the integration of MPLS style backbone across the entire multi-site network. At this point in the project, the internal infrastructure was already fully functional. VLANs were configured, OSPF was exchanging routes dynamically between cities, and the HCP was assigning IP addresses automatically. However, the network was still isolated from the outside world. This stage focused on giving the corporation controlled access to the internet and exposing specific internal services publicly. So for the requirements of this stage, the professor asked us to configure static NATs with the internal servers that needs to be publicly reachable, configure the dynamic NAT overload for employee internet access, assign public IP blocks on each ISP router, connect each corporate router to an ISP, integrate NAT with OSPF and MPLS style network, and test both internal and external connectivity. This step essentially made the network behave like real organization where some internal services are reachable from the internet. The project used a simplified MPLS style model in which each office connects to the MPLS cloud. The cloud provides intercity connectivity. ISP routers act as border routers between the corporation and the public network. This is similar. This is similar in how the real services providers offer connectivity to enterprises. The first NAT requirement was to create static NAT entries for internal servers so that the public clients could reach them. This map included the Ciudad de Mexico web server published to its public IP, the FTF servers hosted in Guadalajara, Saltillo, Querétaro, and Silao. For example, in Ciudad de Mexico, we mapped the IP NAT inside source, the static 172.16.02, 152.78.211.10. This means that any external client going to the public IP is redirected to its internal server. We repeated this process for each production center using the public IP ranges assigned by the professor. In addition, to the public servers, employees in the corporate network also needed internet access. Instead of using one public IP per employee, we use dynamic NAT overload, also known as PAT. This configuration allowed us hundreds of internal devices to share a single public IP while still maintaining unique communication sessions through the port translation. The configuration used was IP NAT inside source list NAT / ACL, interface serial 010 overload. This is exactly how most organizations provide internet access to office users. So now each ISP router had to be configured with the designated public IP block, which this router served as a gateway between the simulated internet and the internal corporate network. They hosted the public IPs from NAT translation, external connectivity tests, public access to corporate servers. They also had static routes pointing back towards the corporate networks. For connectivity testing, the section required extensive testing to ensure everything worked correctly. Internal services, internal tests, like PCB to server pings, office to production center, intercity routing through OSPF, DHCP verification, route propagation across MPLS. And external test is HTTP access to the Ciudad de Mexico web server, FTP access to each production center server, public to private connectivity via NAT, and private to public browsing using overload. All internal and external connectivity tests were successful. Servers were reached only through their public IPs, and employees could reach the internet using NAT overload. As you can see here, in this part, you can see, here, you can see all the pings that we did. We did some configurations for the IPs. We did the show IP interface brief, so we can see the IPs. I'm going to go down where the pings are. You can see all the tests that we did here. This is all from the problem situation 06, where we did all these internal and external connections. You can see all here the IPs from Ciudad de Mexico headquarters, the internal tests, the pings for the getaways, the ping to the server, the IP configuration server to the gateway server's VLAN, all these pings to the Ciudad de Mexico public server. From Guadalajara, we did the ping gateway, ping from the Guadalajara to PC server, from Ciudad de Mexico internal IP. Now we did the internal Guadalajara production center, the ping its gateway, all these external pings, and yep, with NAT and MPLS fully operational, the network was publicly reachable and ready for service delivery. The final step was securing the network using extended ACLS, which is the focus of Section 5. Now I will move to Section 5, which addresses one of the most important practical parts of the entire project, the implementation of security schemes using extended access control lists. Up to this point, the network was fully functional, stable, and connected to the internet. However, it was also fully exposed. Any external device could, in theory, attempt to access internal servers unless a proper access restriction were applied. This final section focused on enforcing security policies at each border router so that only authorized types of traffic could reach the public. Exposed servers located in the production centers and in Ciudad de Mexico headquarters. The professor required us to implement a basic security scheme based on the growth requirement document, apply external ACL tailored to each site public-facing services, configure this ACL specifically on the one-facing interface, permit only the necessary traffic and deny all the other traffic to the servers, ensure the internal corporate routing remaining functional, and performing a new round of internal and external connectivity tests. This means that the security solution needed to protect corporate network would be without affecting legitimate communication. The key to this stage was understanding that every city had different services exposed to the internet, which means that each location needed a unique ACL designed to match only the allowed traffic for its public server. We applied each ACL inbound on the interface that connects the corporate router to the ISP routing. Here's the reasoning. Inbound ACL of one interface equals the traffic filter before entering the enterprise. Only necessary ports should be allowed. All the other protocols should be denied, and internal routing of PF and NAT must remain unaffected. This is exactly how real enterprise border security works. ACL per city. So in Ciudad de Mexico, we have a web server ACL. The Ciudad de Mexico server hosts a web service that must be reachable from the internet using HTTP port 80, HTTPS port 443. Therefore, the ACL name Ciudad de Mexico infilter included the permit TCP any host public IP equal 80 equal 443, and deny IP any host. Permit IP in any for everything else not targeting the server. This ACL ensures the web server is visible externally but protected from any unwanted traffic. In Guadalajara, we have FTP server ACL. The Guadalajara production center hosts an FTP server that requires port 21, port 20, and ICMP for diagnosis diagnostic pings. Sorry. So we created the ACL Guadalajara in filter, allowing exactly this: permit TCP any host, EQ 2021, permit ICMP any host, deny IP any host, and permit IP any. Anything other than the FTP and ICMP, sorry, was blocked. For Monterrey and Saltillo, also host a FTP server. So Monterrey's border router needed similar routes: permit port 21, port 20, permit ICMP, and deny all others IP to the public server. For Querétaro, we also exposed a FTP service. Its ACL followed the same pattern as Guadalajara and Saltillo. So it's able to assign public IP. For León and Silao server was also FTP based. The ACL allowed only the required ports and ICMP blocking anything else targeting the server. Once the ACLs were applied, we tested internal connectivities. The PC could still reach their local routers. The VLAN's intercommunication remained intact. OSPF neighbors relationship were unchanged. All office could reach each production center via private routing, and NAT functionally remain correct. For external, the public side PCs could access only to the intended services. The Ciudad de Mexico web page loaded correctly from the internet. FTP connections to all production centers succeeded. Pings to all public IPs worked, and the night protocols were confirmed to be blocked. And those, we can see them right here. This is the problem situation part 7. Here are the connectivity tests from PC Ciudad de Mexico to server. And we have the password here. Here we have the internet page. We also have another one here. We can see here that the ping was successful as well. From Guadalajara, we have it from Guadalajara Gateway. Then we have the ping from PC Guadalajara 01 to VLAN 10. Another ping from PC Guadalajara PC 01 to Silao FTP server. For the access, internal from the ping from PC internal Guadalajara to public FTP server. Though we have the ping from this IP address from the PC Internet Guadalajara, and we have them all here. All the connections, the pings were correctly functioning, as you can see. So with the ACL implemented and validated, the multi-site network was officially completed, scalable, fully interconnected, externally reachable, and properly secured. To conclude, this project allowed us to design. This project allowed us to design and implement a complete multi-site enterprise network. We start with the physical and logical design, then move to the VLAN segmentation, OSPF routing, DHCP service, NAT integration, MPLS style connectivity, and finally the implementation of secure schemes using ACLS. All internal and external tests were successfully, as you all can see, and the network operates as functional, scalable, and secure corporate environment. On behalf of the team number 1, thank you for your attention.